So, good evening, everyone. I am Saurav Sahu, a fifth-year PhD student in the Department of Material Science and Engineering at IIT Delhi. So, I'll be taking this NPTEL-PMRF TA lecture on Phase Equilibria. So, we'll be moving over to the contents of the second week of the lecture. So, I'll be sharing my screen. All right. So coming over to the contents of the second week of this course. So we have started out with the calculation of configuration entropy, and we have seen that how in a binary mixture of solid solutions, we have seen that an addition of a solute to a solvent increases the configuration entropy and hence causes reduction in the free energy of mixing. So we'll be going ahead and just reviewing the concepts that have been covered in the past 4 or 5 lectures in the past week. So to start with, we have seen in lecture 6 the calculation of configuration entropy. So we'll just quickly brush through that. So okay, so we have seen then when you take a two-component system containing A and B, let's say, and when you just mix the two elements of pure A and pure B, so in the initial mix the entropy is 0 because we have not mixed it yet. But however, after we have mixed it, so my entropy of the system is calculated according to Boltzmann equation, wherein we take the number of possible microstates of the system and for a given microstate, and then we apply it in this formula, and where K is the Boltzmann constant and W is the total number of configurations possible, microstates possible for a given microstate. So let's consider a system wherein we have Na, number of A atoms, and Nb, number of B atoms, right? So now if I have a total of Na plus Nb atoms, and my whole formula starts out with the calculation of the total number of ways in this the total of Na plus Nb atoms can be arranged. So by combinatorics, we know that if we have a system containing Na plus Nb atoms, and let's say we have a total number of sites as Na, so the total number of combinations that we can make with the system is this, which on expanding, we know by mathematics, gives us this. And we just take a difference between these two, which is nothing but Nb, the number of B atoms. And this is actually the W parameter that we see in this equation. And yeah, and we have seen that since this is quite an extensive equation, if you plug it in the logarithmic, it will actually be very cumbersome. So we apply certain approximations so as to get a simplified version of this equation without losing much precision. So the approximation as such is proposed by James Stirling, So we'll see. So the change in entropy upon mixing is given by S final minus S initial, which is, since S initial we have seen it was 0, since it was 0, so we have the total change in entropy is contributed by the configurations of the atoms, or the randomness of the atoms which we arrange in a mixture of or the solution. So upon expanding, we get this. Okay, and since we know ln A by B can be written as ln A minus ln B, so we can just write the same as since we again know that ln A into B is nothing but ln A plus ln B, so we have so this A is in subscript, by the way, which is the total number of A atoms, and since we have negative sign, so upon expanding we have negative factorial. Great. So again, now applying, so now what is important is to note that since this is quite very cumbersome, because we know that the factorials they tend to multiply many folds, and if you just take logarithmic of that, that will be really quite complex. So we apply a very simple approximation proposed by James Stirling. Which says ln x factorial is given by x ln x minus x. So I just use the same formula for my system, and what I do is I just expand it. So in that case, ME plus MB is nothing but x here, minus NA, since it's negative, so it's negative here, and then minus NA ln NA plus, because it's negative, plus NA, and minus ln NB plus, again we have negative at the outside, so we have this. Now we can see that we have negative and positive cancellations, and we end up with this. Sorry, this should be N. So again, we just apply the properties of logarithms, that ln A minus ln B is ln A by B. So if I just expand it with keeping NA as common, so we have this, right? So moving ahead, what I'll just do is I'll just reverse the ratio. So ln x inverse is nothing but minus of ln x. So I'll just inverse the ratio and I'll just collect the negative outside. So we have minus k, and on the inside we'll have Na. Okay, so now we know, since we know that the Boltzmann constant is nothing but the gas constant divided by n naught, which is the Avogadro's constant. We should write n constant to be consistent with the lectures. N is equal to 6.023 10 to 23 atoms. So we just evaluate the value of k here. So that will give me minus k and a. So what I have done is I have divided Na, that is Avogadro's number, and I have multiplied it in the numerator. So this Na, that is the total number of A atoms, by Na, which is the Avogadro number of atoms. Okay, so now we can quite clearly see what we have here is nothing but the mole fraction of A, that is chi A, and this is the mole fraction of B, that is chi B, and here this is basically the number of moles. So we have the number of atoms of A divided by the Avogadro's number of atoms, which is nothing but the number of moles of A, and we can write that as number of moles of A, small n A, and this is ln chi A, plus number of moles of B ln chi B. So this is giving me the free energy change upon mixing, and since we are interested in molar quantities, so since in the last lecture we have seen what are the intensive and extensive variables, so if we just divide it by the total number of moles, we get the free energy of mixing per mole, right? So for that we just divide by the total number of moles, which is nothing but Na plus Nb, because we have A and B components in the system. So if I divide it by the total number of moles, okay, so this if I just take this part inside, what I'll have is what will be left out with this. So Na by Na plus Nb is nothing but the total number of moles of A by total number of moles in the system, which is equal to the total number of atoms of A by total number of atoms of the system. So it's nothing but the mole fraction. And so I'll just write what I have mentioned here, since chi A by definition is the total number of uh, is the mole fraction, so it's the total number of moles of A divided by the total number of moles in the system, right? So this is what we have evaluated here. So in this case, we have just divided Na by Na plus Nb, so we have chi A inside, and just k into Na. So in this equation, we have seen that since the Boltzmann constant is nothing but R divided by Na, so k into Na is nothing but R. So this will ultimately give us the free energy of mixing per mole as negative of R chi A not chi A plus chi A not chi A. So it was covered in the lecture, but the comprehensive derivation was left as an exercise. So you can just try it out and you will get the same equation here. So this is what we get, and this is called as the configurational entropy term. So this is the reason why the nature prefers systems in the pure state, because a small amount of solute in the solvent actually increases this term because of the disorderness, and that's the reason we have lower free energy upon mixing and solute in the solvent. Okay, so moving ahead, so we have seen the calculation of configuration entropy in a system and how it affects so this is configuration entropy configuration. Okay, so now we'll see, since for an ideal solution we know that the delta H mix, because we take a lot of assumptions that they have the same molar volume, the same crystal structure, and so the entropy change upon mixing is 0, and also there is no preferential bonding between AB atoms as compared to AA or BB atoms, so it's completely the same. So the tendency to form AB atoms is same as AA or BB atoms, so the change in entropy, the change in enthalpy, is equal to 0, because we don't have any sort of preference for any type of bonding, right? So it will the system will either absorb it or emit it upon mixing. So now if I just plug it in the delta G mix, which is nothing but delta H mix minus T delta X mix, and please be wary that we are all considering per molar quantities. So this is nothing but the change in the enthalpy per mole. So this is change in the entropy per mole. So we can just plug it in here, and since this is equal to 0, and this is for ideal solutions. So the delta G mix term is R T chi dot xl plus chi b dot. Okay, so this is for an ideal solution. And how does it vary? So if we just take the plot, so this here is B, this is A, and this is the mole fraction of B by B. So this is 100% B here, and this is 0% B here, right? So 100% A. So mole fraction of A increases this way, mole fraction of B increases this way. So now since we are plotting del G mix, so this is not the molar free energy, rather is the change in free energy upon mixing, and how we're getting is something like So for a given composition, for a given value of chi B or chi A, because this both are complementary to each other. So since chi A plus chi B is equal to 1, both are dependent. So chi A is dependent on chi B. So if we just fix one, we will be having this the other one also fixed, right? So if you just take a given part of B in A, so there will be certain reduction in the free energy, and that is where we will have our equilibrium, right? And since you already know from the first week lectures that the change in free energy is given by this equation, wherein this term is the change in free energy after. So this is the initial, this is the final free energy, right? And the initial free energy, since it was nothing but mixtures, we have just taken A and B and we have mixed it manually. So the rule of mixtures will be valid. So the rule of mixture tells us that the free energy upon the free energy, initial free energy of the system on just mixing, the initial free energy will be chi A GA plus chi B GB plus whatever we have calculated the configurational curve. Right. So this is the term that is getting added up. Or in sense, because the directions, because the sign convention will be negative, we will see that the G2 is actually lower, and that's the reason why delta G mix is negative, and this negative value is basically dependent on the temperature. So if we take a system which is at a higher temperature, let's say, so maybe if we take a system which is at a higher temperature, the del G value, this, right? So this is at T2 and this is at T1, such that T2 is greater than T1. So we will have the net reduction in the free energy of mixing at higher temperatures just because of the configuration entropy term, because higher temperature prefers more disorderliness in the system, right? Okay. So just close that. Okay. So quickly going through next part. And also, instead of taking the free energy change upon mixing, if we take the molar free energy, how will the graph look like? So since it was already mentioned that the molar free energy plots will have a pure A component here and a pure B component here. So the molar free energy will look something like this. So initially there will be certain amount of free energy intrinsic to A, and there will be certain amount of free energy intrinsic to B, right? This is in the intrinsic state, we will not mix them yet, and this is how the rule of mixture tells us. So we just, if we take this and maybe somewhere here, we have just taken a composition having, let's say, chi B amount of B in the system, right? So upon mixing, what will happen is this will be a curve like this, right? So it should be like this. So as per the proper definition, this curve should be actually parallel to the y-axis near the free or near the pure elements. So just for the sake of representation, it has been shown that it is intercepting, but it's actually not, right? Okay, so this is at a temperature, let's say T1. Okay. So what will happen if we just increase the temperature of our system? If we increase the temperature of our system, what will happen? The intrinsic free energies also will reduce. So this is our GA prime, this is GB prime, and this is a temperature, right? Okay, so this is GA prime and GB prime. We will have something like this. Okay, this is a T2. So not only we have a reduction in the intrinsic free energy, but also upon the change in the, but also in the change in free energy upon mixing. Okay, this is delta G. Mix at higher temperature. This is delta G mix at lower temperature. So this is a T1, and this is a T2. Okay, and this the amount by which it varies is actually the delta G mix. Okay. So this has been covered in the lecture. So moving on, the chemical potential was briefly discussed. So chemical potential of a system, or rather a element in a mixture. So if we maintain the temperature and pressure as constant, so how will the free energy of my system change upon tweaking the composition of one component, right? So that is what my chemical potential tells us. So this here is the chemical potential of A in a solution of AB, which gives us there is a change in the free energy upon slightly varying the composition, slightly varying the amount of A, that is the number of moles of A, such that my temperature and pressure is constant, and adding DNA, or the very incremental amount of N in the system, does not change the composition. So this is another assumption that we take, because if composition changes, the mu A also changes. Mu A is highly composition dependent, so it is if there is a variation in the composition, significant variation, so the chemical potential also changes. So this another term of another way of writing was right? And this is taken at constant temperature, pressure, and NP, where NB is nothing but the complement, because we are talking about binary solutions. So Na plus NB is the total number of moles in the system. So NB has been kept constant and Na was increased. Okay. So Karthik, can you please mute yourself unless you have something to speak? Thank you so much. So we were discussing about the chemical potential of a solution, chemical potential of an element in a solution. So we have seen the formula. So we'll be going on to the numericals. Just before that, I just want to brush through the equations that have been discussed. And this is the change in free energy, the generic case, right? So we have seen that for one component system, we don't have this summation part, we just have VdP minus SdT. But for a multi-component system, where the number of components are more than one, so we'll have this equation of the change in free energy. So now extending this, we have seen how the chemical potential will actually look like in the graph, right? So if you have A here and if you have B here, the fraction of B increases this way. So there is this GA and there is GB, let's say here. And we have this free energy on mixing this way. So if we just take a tangent. So this here is the point where my free energy is minimum. So this is actually the amount which will be stable in equilibrium. And if we just take a tangent at this point and let it cut to the intercepts, this will give me the chemical potential of A. And we'll see in one of the numericals ahead that how this can be derived. And by definition of the formula, UA was nothing but the primary DNA, which is GA, that is the intrinsic free energy of A, plus log chi A. And this can be, the same thing can be written for B as well. So this distance is minus RT log chi A. And same goes for here all as well. So this distance is minus RT log chi A. And this is the chemical potential of B, UA and UA. Looks like M perhaps. So we'll see how this we can apply in numericals. So we'll see that ahead. And now we come to the regular solutions. So we have already seen what are regular solutions, right? The non-ideal cases, the deviation from ideality, regular solutions. So we have seen that for ideal solution, delta H mix is equal to 0, right? But for regular solution, we have certain changes, right? We have changes in the molar volume. So del Vm is not equal to 0 in real cases, right? So we also have we have differential difference of a particular bonding for a particular bonding pair. So that tells us that the bond energy AB might not be equal to AA or BB. So earlier we have seen for ideal cases, the bond energy of AB in a system of mixture of AB is equal to AA bonds and BB bond energies, which was the reason behind the uniform distribution of AA and BB in the solid solution or mixture. But in actual cases, in the regular solution, we see that this is not the case. So either the bond energy of AB should be higher or lower than the HOMO bonds, the AA or BB bonds, right? And also we have assumed that the crystal structure also changes. So upon addition of a component, there might be an increase because the volume is not conserved. So there could be certain change in the cell of the structure, so that we have a change in the crystal structure, and that all those regions contributes to the non-zero values of the enthalpy, right? So if delta H is greater than 0, we have seen that this is endo. While if delta H mix is less than 0, we have exothermic case. Okay, so then we have seen in the case we apply a concept called as quasi-chemical approach. So for regular solutions, we apply this quasi-canonical approach, right? Wherein we assume all the changes happen. The changes that we have mentioned here, they all are allowed, which were forbidden in the case of Alexander. So if we just take EAB is the number of hetero bonds, number of AB bonds with bond energy epsilon or EAB. And similarly, EAA is the number of AA bonds, which is epsilon AA. And EBB similarly is the number of BB bonds, is epsilon BB, right? So initially we have seen that if we just take all those components of A and B and just we just let them mix, right? So what will happen is they will form bonds, right? So and this bond will contribute to the internal energy. And the total internal energy we have seen in the first week, the total energy is they have a contribution for kinetic energy and potential energy, right? And this potential energy also has a component from interatomic bonding. So if there is a change in bonding upon mixing, so there are AB bond formation, right? So this bond energy potential will change, and then this will affect the internal energy. So we'll see that how this internal energy changes. So this U final, the change in the internal energy upon mixing, the final internal energy upon mixing can be given by, so we have AA number of atoms with bond energy EAA, and we have BB atoms, the number of PBB and with bond energy EBB, and similarly we'll have AB atoms, the number of AB atoms is PAB and their bond energy is EAB. So this is after mixing, and immediately before mixing, what was the initial internal energy? Well, it was something similar to this, but there should not be any AB, right? Because we have not started the mixing yet. We are just taking A and B together, and then at the very snapshot, we have AA number of atoms with bond energy AA. Although this E prime AA might not be equal to EAA after mixing, right? Because we have considered before mixing and after mixing, and because of the change in the internal energy upon mixing, we'll have more AB bond or less AB bond formation depending upon the enthalpies of bond formation, and so the number of AA atoms or the homo bonds might not be equal, right? So this is understood. And similar for PBB, so P prime BB might not be equal to PBB. So this is the initial configuration just before mixing. So what is the change in the enthalpy upon mixing? This change in, since we have seen that enthalpy H is equal to U plus PV, right? Since H is equal to U plus PV, so delta H is equal to delta U plus delta PV, right? We will write it a bit clearly. So this delta H is equal to delta U plus delta PV for a microscopic change. So delta H, we are not, there is no pressure volume work term here, so this is nothing but 0. So whatever change in the internal energy will contribute to the change in the enthalpy of one system after mixing, right? So this will give me delta H mix as PAB. So there is a derivation wherein we get actually the difference in terms of EAB or epsilon AB and epsilon BB, but for the sake of conciseness, I have just skipped that part, because I mean, you can go ahead and just subtract this 2 and you will end up with this term E, where we say E as change in the bond energy between the AB bonds and the average of homo bonds. These are the homo bonds. We take an average of it. And what's the difference between this bond energy of an AB and the bond energy of the average bond energy of the homo bonds? And this certainly tells us that my enthalpy change on mixing is non-zero, right? So this is non-zero. So which sign is my delta H mix? Is it greater than 0 or less than 0? We don't know. So that actually depends on the sign parameter. Okay. So what is that? We'll see. So this PAB term, the total number of AB bonds can be given by, so just imagine the total number of AB bonds is the product of the mole fraction of A and B. Okay. And the mole fraction is nothing but the number of moles divided by the total number of moles, right? So if I just multiply it with the Avogadro's number and A, right? So that will give me the actual or the exact number of bonds of AB, exact number of AB pairs. And since we multiply with this by the total number of bonds per pair, we have the total number of AB in the system, right? So where MA is equal to atoms per mole, and C is equal to number of bonds. So this is the total number of bonds in the system, right? So chi A, chi B, so we will put in this line. Chi A, chi B is the total number of moles of AB, and if I just multiply with the Avogadro's number, this will give me total number of AB bond pairs. If I just multiply it again with the total number of bonds per pair, it will give me the total number of bonds, right? Which is nothing but PA. Okay, so just plug it in our enthalpy change of mixing equation. So we had this, right? So we have Z and A, where N is our Avogadro's number, which is a constant, Z, chi A, chi B, E. And since for a given composition, we have E, where E is equal to nothing but the change in the bond energy between AB bond and the average of AA and BB bonds. So for a given composition, the bond energy of AB will be constant, and so this will also be constant, right? So if this will give me omega chi A chi B. But this omega is an important parameter. Business constants. Okay. And this omega is the one which determines the sign of delta H mix. Why is that? Because the mole fractions is always positive. It's less than 1, between 0 and 1, and the product of two mole fractions is again positive. So the sign of the delta H mix will be determined only by the omega. The omega term, and this omega term is nothing but this terms. So again, the Avogadro's number is positive, the total number of bonds per pair is always positive, should be a whole number, either 0 or greater than 0. So which tells us that the E parameter is the one which is determining the sign of delta H mix. This is very important to note, because for our solution, we just have to keep in mind that what is the sign convention of E for that solution, and that will give me, if my solution is stable or not, because this parameter directly affects the enthalpy of bond formation. Okay. So we have seen that for omega greater than 0, that means E greater than 0, for E greater than 0 tells us that my AB bond is not favored over EAA or EBB. This is because if my free energy, the change in the bond energy is higher, that means after the bond formation of AB, the bond energy is actually increasing, which is not good because the system is not stable. That means so the bond AB is not favored. So hetero bonds are not favored in this case then. So how will that curve look like? So we will have the increasing mole fraction of AB this way, AB. You can just change the color here. Now, as I said that omega is greater than 0, so this is the reason why my delta H mix is positive, as this controls the entire sign of my delta H mix, so that this delta H must be positive, right? And the slope of it will give me omega. How is that? So if I just take an incremental increase or change in my free energy of mixing, rather, so the enthalpy of mixing, sorry, and I derivate it over a very small amount of A. So A is the solute in the solution, B, AB, and if I just see, I get this. So just remember what was the formula? The formula was this, right? So I can write this as dou HC times omega chi A chi B. And since we are considering two component system, so chi A plus chi B is equal to 1. Therefore, chi B is nothing but the unitary complement of chi A. And if I just derivate it, give me dou delta H mix by dou of A. Omega is a constant here. 1 minus 2 chi A, right? So this is important. So this tells us that just to write it down. So okay, this is 2 not 3. Okay, at chi A is equal to chi B as half. So for an half and half case, half of A and B, we'll see that this term is actually 0, right? So value delta H delta X is equal to 0. And another case is when my mole fraction of solute is very small. It tends to 0. It's very small. It's towards this end, towards the left end. The A is very small. In that case, my slope, right? So this is nothing but the slope in that plot is omega, which is the slope. So this here, if we take at the very starting point where chi A is very small, chi tends to 0. The point, sorry, chi tends to 0, then slope will be omega, right? In this omega term is positive here, as you can see, because E is positive. Okay, so this is another concept that we have seen in this week's lecture. Okay, so now we'll move ahead and discuss the change in free energy quickly. What is the change in free energy upon mixing in a regular solution case. So the derivation has been carried out in the lecture. I'm not going to do that. So what will happen is, so the attachments we have seen in the previous case, it's nothing but omega chi A chi B, and this was already there in our ideal solution case as well. So RT chi A non chi A plus chi B non chi B, right? So now we know that the free energy change upon mixing. So the molar free energy after mixing is G2 is equal to G1 plus del G mix, and G1 is given by the rule of mixtures. So chi A Ga plus chi B Gb plus omega chi A chi B plus RT times chi A non chi B plus chi B non chi B. Okay, and this term is what we have seen is coming as extra. So this extra term upon deviating from ideality. Right. This is the term that is coming as extra. Okay. Right. So you can go ahead and do the derivation. We'll see in one of the numericals or as well. And on doing derivation and comparing with our earlier equation, where mu A was termed as the coefficient of chi A, so that will give us Ga plus 1 chi A plus omega 1 minus chi A square. Similarly, the chemical potential of B can be written as Gb plus RT1 chi B plus omega 1 minus chi B square. Right. So this is pretty simple to derive. What we have to do is we just have to compare this equation with the one that we have already got for the case of ideal solution, and we see that the coefficients of comparing the coefficients, you can get the chemical potential of A and B. Okay, so this leads us to a few important cases that we see ahead. So case 1 tells us when my omega is less than 0 and temperature is high. Case 2, when omega is less than 0 and temperature is low. Case 3, when omega is positive and temperature is high. Case 4, when omega is positive and temperature is low. So we'll see that this is a very special case. So So this was the case 1 where omega was greater than 0 and temperature was high. Sorry, yes, it was opposite. Omega was less than 0. So case 1, omega is less than 0, temperature is high. We see that as carbon increases, delta H mix is like this. Delta T delta X mix, something like this. So overall it gave us highly negative. This is delta G mix. This is okay. So for case 2, where we have omega less than 0 but temperature is low. If temperature is low, as we have seen in our previous case, yeah. So low temperature, basically we will have the free energy will be less negative, right? So this is also what we see here. So omega is low, less than 0. So of course my free energy curve will go towards the negative side. My delta S mix will not be very deep, it will just shallow. And as a result, my pH will change with the solution. And also going to be shallow. So it will have lower driving force. As compared to this one, it will have lower driving force because the temperature is lower, right? Because the temperature is lower. So similarly, we see what will happen in the case when my omega is positive and temperature is high. Okay. So if my omega is positive and temperature is high, omega is positive, that straight away tells us that my curvature of my enthalpy should be positive. Because omega is greater than 0, E is greater than 0, so AB bonds are not very much favored, right? But my temperature is high, that means my free energy coming, the entropy, the configuration entropy term is highly negative, right? So, very deep. Let's go like this. As a result, still have a net negative delta G mix. And even though my bonds are not favoring the solutions, the entropy term is saving the day. So because of the high temperature entropy, it will favor the mixing. Case 4, when omega is greater than 0 but temperature is low. Now this is a very peculiar case because earlier entropy was allowing the bond formation. Omega is greater than 0, so we have that curvature of delta H mix is positive. And since my configuration entropy is not very strong here because the temperature is low, so let's say I have T delta S mix as like this. So you see initially I have not shown it here very clearly, but the slope of my entropy change T delta S mix graph will be very, very high, and the slope, as you have seen, of this is limited to omega only. So this term is highly strong at the edges, and that's the reason why we have the net change in free energy as negative here. Then it goes to positive, and then it goes again back to negative at the edges, just because the slope of the T delta S mix is very, very high at the edges. So that's why we have stable solution forming in either of the ends, right? In this and this end, we have stable solution forming, but not in this case. So by the way, these are all P and P components. I have not written, but this is easy to understood. And the mole fraction of V increases this way. Okay. So this was one of the consequences of the sign of the omega term. Right. Now we'll quickly go through the activity, the last part covered in this week's lectures. Activity. Now what is activity? Activity in case of dilute solutions. Now what do you mean by dilute? When the amount of solute, because a solvent has some solute added in it, but the amount is very low, right? Then we call it as dilute solvent. The dilute solution. So in this dilute solution cases, so whether or not my elements involved in the solution, do they have a tendency to isolate, or do they have a tendency to go back into the solution? That is given by the activity of the elements. Okay. So we have seen that even though in the previous slide we have seen that even though a delta H mixing is positive, every system can tolerate small amount of impurities. Small amount of impurities, and this is because and only because of configurational entropy. Right. So the activity is, the equations are very familiar because it looks something like very similar to what we have studied. So instead of having the mole fractions of A in this chemical potential equation, we have this. Okay, for an ideal AB solid solution. So the activity, again, it depends on the tendency of the elements to either isolate or to go back to the solution. So for regular solution, we have seen that for regular solution, we have seen that the activity of ith component is not equal to the mole fraction of the ith component. Okay. For ideal solution, they are equal. So the activity can be greater than the mole fraction or less than the mole fraction, depending upon the delta H mix. Right. So this parameter determines the delta H mix is determined by omega, which is determined by E. So this E parameter is very important in regular solutions because it ultimately determines the activity of the elements as well. Okay. So we also see the plot of how it looks. Right. A, B, carbon. So this is Ga, this is Ga, the rule of mixture. This is initial is equal to Ga, Ga, after mixing, this is how it is. Okay. And if we just take the tangent at this point, the intercepts give us wave C, give us the chemical potential, right? And the difference here is the mix, and G2, or the final this the final curve shown in red is G1 plus del G mix. Del G mix, the difference in G1 is chi P Gv is chi P Gv plus the omega 2 chi P plus RT chi P not P is chi P. Okay, so this is the equation, the free molar free energy of the solution after mixing, before mixing, and difference is del G mix, right? And this is del G mix, by all these terms as the del G mix. And in this again, the difference is given by minus RT non EEP is minus RT non EEP. Okay, so this is the intercept difference. Alright, so this is what we now for regular solution we know that omega A is equal to G plus 1 minus chi A whole square omega is RT mod chi A, right? And this term is what we are saying is equal to RT non EE, because this is what we are getting here. So this entire term is this thing. So we just equate them. Okay, and this will give us non chi A is equal to omega 1 minus chi A square by RT. So this gives us a few conclusions that if omega is equal to 0, when omega is equal to 0, when epsilon AB is equal to or the bond energy between AB is equal to the bond energy, average bond energy of A and B. In that case, my activity is equal to my mole fraction, and that is very important, and this is what causes ideality, right? In ideality, the omega is 0, there is no omega term, but in natural solution there is omega, it's non-zero. That's the reason my activity is not equal to any mole fraction. So as a consequence of this, we have the plot between A and B, and we have have seen because the activity there's upper bound to that 1. So let's say this is the activity of B. Okay, so activity of B in 100% A, this is 100% A here, so activity of B is 0, and activity of B at 100% B is 1. So there will be a line like this. Okay, so maybe not on it straight. Okay. So this is the case where activity of B is equal to the mole fraction of B, which is Raoult's law. And we have seen a special case where individual cases where my delta H mix is greater than 0 or omega is greater than 0. So my AB bonds are, in this case, AB not preferred. So that's the reason we have higher activity. And higher activity says that there is a very high tendency to segregate out from the solution. Whereas if we have delta H mix less than 0, omega is less than 0. So my E parameter is less than 0, which tells us that AB bond energy is lower than AA or BB. So AB is preferred. So activity is lower than my linear line, and that tells us that will not segregate out, will not isolate from the solution. Okay. So, and the coefficient we have seen that gamma I is equal to AI by xi or chi I, and this is called as the activity coefficient. Okay, and for Henry's law, Henry's law tells us for a dilute solution of A in B, that tells, which means my limit chi A tends to 0, the activity coefficient rather, the activity coefficient of A in B. So A is the solute here, right? And B is the solvent here, which is higher in amount, and A we are taking negligible amount. So is given by chi A is equal to AA by chi A, and chi B will almost be 1, since non AA by chi A is approximately equal to omega by RT, because XA tends to 0. So we have seen this equation that when XA tends to 0, this term can be neglected. So omega by RT is what we are getting, and omega by RT itself will be so small, so that we can consider this since in logarithmic of A, we can consider this as A. So this logarithmic of a very small quantity, we can just take this, right? So ultimately what it tells us that the activity coefficient of the solvent phase, which is higher in amount, will behave like ideal, whereas the activity coefficient of the solute will not. So that's the Henry's law and the Raoult's law. Okay. So we have also seen this equation with delta H mix, the sign of it changes the behavior of the activity. Ultimately, we have also seen in the final part of the lecture, we have seen the degree of ordering. That is the final part we will discuss. This degree of ordering is given by S parameter, which is the number of AB bonds which is observed minus the number of AB bonds at random divided by the number of AB bonds maximum which is possible minus the number of AB bonds taken again at random. Okay, and this thing is completely the disordered part of it. Disordered part, and this thing here is the complete ordered part. Okay, so this will give us the degree of ordering, and then it can tell us whether if it is the ordering is along a short range or the ordering is along a long range. So we have three cases where S can be equal to 0. When this, you can say when this is 0, it is completely disordered, right? And S is let's say it is negative. It can't be negative though, it's always positive, so it is small positive. So we have short range ordering, like in classes. In classes we have loss in order beyond the tetrahedron or the smooth cell ordering inside of the class, so beyond that it is completely disordered. And if it is large positive, large positive, or even 1, it's completely ordered. Okay, or long range ordering, to be precise. Okay, so I guess that is all the concept we had discussed in the past week. So we'll quickly glance over a few of the numericals that I have curated out of out of the exercises from the books, and only the concepts that have been covered in the weeks will be discussed for the numericals. So we start out with the first question, which is determine the number of distinguishable ways of arranging 2 black balls and 2 white balls in a square array. Right. So this is a very rudimentary or fundamental combinatorics problem. So the number of ways of arranging 2 black balls. So number of black balls is 2, and the number of white balls is 2 as well, right? So the number of ways of arranging 2 black balls and 2 white balls in a square array of 2 by 2, let's say. Okay, so we have seen theoretically its concept is very similar to the formula of configuration entropy. We have the W term, which uses a similar concept. The number of So just assume the balls are atoms here. So the number of ways the atoms can be arranged is given by the formula and is what we will use to find the number of ways of arranging these two black and blue white balls, right? And since we are not considering equivalent cases, so it has to be distinguishable. So every configuration has to be distinguishable. Ways of arranging two black and two white balls in a, let's say, a 2x2 square. Is so MB plus MW factorial divided by MB factorial and MW factorial, right? So we have what 2 plus 2 factorial divided by 2 factorial into 2 factorial, which is 4 factorial by 4. 24 by 4 is 6, right? So we can quickly show what are the 6 configurations possible. So it's better if I just draw it. So just imagine I'll shade them to represent the colors. So to quickly verify, you can make a structure like this, and you can repeat it 6 times. So we'll see, let's say I'll just shade it to represent it as black. Okay, so first configuration, I'll have black like this, and black also. So this is my configuration 1. The second configuration I might have, let's say, black here. Configuration 2, crisscross. This is configuration 3. Again, I think we thought was it crisscross because it is distinguishable. Fifth one, configuration 5, and sixth one, configuration 6. Okay, so these are the total number of ways of arranging two black and two white balls in square array. So coming over to the second question. So by definition of chemical potentials, show that you know, A and B can be obtained by extrapolating tangents to the GX curve. Okay, so we know that we just quickly adapt this problem. So we know that the free energy is given by this way. Okay. dN. So if I have increase the composition by n moles, so this should also be dG8 plus B. So this is divided by the total number of moles. NA plus NB. Okay. The left hand side of the equation here is the free energy change per mole. So we have free energy change per mole of solution, and therefore it can be written in this manner, right? And these are, what are these? These are the changes in the mole fraction, right? So these are the changes in the mole fractions of A and B. Decay A and decay B. The equation now can be written as dG. So if it was per mole, so if we just write dG as per mole notation, so it's equal to, if we divide by total number of moles, we get per mole. So we can have mu decay A plus mu B plus G by decay B, let's say, is equal to mu A decay A by decay B plus mu B, which is equal to minus mu A plus mu B. Now why is that? Because sky A plus sky B is equal to 1. If I just derive both sides, decay A plus decay B is equal to 0. Therefore, decay A is the negative of decay, and that is what we have applied here. So, and it's negative, and if I just take both are equally magnitude, so it will just cancel and we will have minus 1, right? So, and we also know that G is equal to chi A plus B by D, right? So with this comparing, we get, so this gives mu B is equal to, from this I can get mu B is equal to G minus mu A chi A by chi B. So I will take mu B as the subject here, and I will take everything to the side. But we're giving, if we just solve this, we give dG by B by B. So this is what we have got earlier. In this case, minus mu A plus mu B, that is minus mu A plus mu B, and mu B is the entire thing, right? So, or if you just expand it, you will get mu A is equal to G minus, so what we get is phi B dg by d phi B, right? I just multiplied this term, right? Graph. And so this is pointer, this is pointer, this is going to be this point is Q, this point is Q, this is phi B, this is B, okay. So from the figure we can say that mu A is what is mu A? Mu A is this one, right? ER minus phi B times QR segment, this QR segment, I just multiply it divided by phi B. So ER minus QR will give you this part, this one, right? And that is equal to PQ segment, and that is equal to OS segment. This one, let's say this is what, this is this. So if you just see the equation, mu B is equal to mu A plus dg by dxb. So this is one of the equations in the book. That gives me mu B is equal to OS line, this mu B line, right? So for S line here plus mu V line here. So this mu V line. Segment is equal to OP segment. This is 2 here, OP, and that is equal to 1, let's say. Then BB is equal to OP segment plus BB segment is equal to PB segment. So here this is the diagonals. Here this is the B. This part is this is the OT B. So this kind of tells us that we can get the chemical potentials of A and B by extrapolating the tangent with the extreme limits. And a bit of a geometry, but it's pretty similar to pretty easy or pretty intuitive to understand, right? Okay, so now we go ahead and quickly see the next question. So derive the formula for chemical potential of elements in a regular solution. Now it has already been covered in the lecture, at least it has been. So maybe I quickly. Well, so we know the formula G is equal to A by A plus B by B. So if we add 1 mole of A and B, so the change in energy will be equal to 1 mole of A and G, right? So that is equal to G. And G is equal to phi A Gb plus phi B Gb, which is the rule of mixture before mixing. And it's a non-ideal or regular solution, so omega phi A phi B plus RT and phi A sorry RT phi A non phi A plus phi B non phi B, right? So now it tells us since phi A plus phi B is equal to 1, I can just write phi A phi B as phi A phi B times phi A plus phi B is equal to phi A square phi B plus phi B square phi A. Okay, and if I just plug in this thing here, and get evaluating, we get G is equal to phi A Gb plus phi B Gb plus omega phi A square phi B plus phi B square phi A, right? Plus R theta RT phi A plus phi B non phi B. I need one more blank slide to complete this derivation. Okay, so now that we are here, I will just take phi A common. What I have inside is Ga plus omega phi B square plus RT phi A. You can work it out. Phi B, just take phi B common. We have phi B Gb plus omega phi A square plus RT ln phi B. Okay. So comparing with equation we have, we just compare this. We know that mu A chi A plus mu B by B is G. Therefore, I will get, if I just draw parallel comparison, I get this is actually the mu A, right? So mu A is equal to Ga plus omega, now phi B is being written as 1 minus phi A square plus RT log phi and VB is equal to GB plus omega 1 minus pi A, that is 1 minus pi B square plus RT log phi. Okay, so this is the derivation that the question had asked in the field. So moving on to number 4, which is the graph. So please bear with me. It has asked that 15 gram of gold and 25 gram of silver are mixed to form a single ideal solid solution. So we have an ideal solution which has been mentioned already, right? So how many moles of solution are there? So we know that the atomic number of gold is 1.97, right? And the atomic number of silver is about it's exactly 108. Okay? So the number of moles of AU is 15 grams. Sorry, I had mispronounced and represented the terms. So these are actually the molar masses. Let's say W, right? The molar units. So so if I divide given mass by the molar mass, I should get the number of moles, right? So 15 by 197 gives me 0.076. Number of moles of silver is 25 by 108, which should give me 0.231. So this is the solution to part A. So what are the mole fractions of gold and silver? So now we have the moles. So to get the mole fractions, it's pretty easy. So we just have to divide the number of moles of gold by the number of moles of gold and silver, right? So 0.076 by, if I add it up, it should be 0.307, which gives me 0.248, or rather 0.25 approximately. And the mole fraction of silver is given by number of moles of silver by number of moles of gold plus number of moles of silver. That is 0.076, 0.231 by 0.307, which is the sum of both the moles, and 0.75, is what you get from calculation. Okay. Next question has asked what is the molar entropy of mixing. Right. So by the formula, you know that molar entropy of mixing is delta S mix is given by minus R pi A log pi A plus B log B. And that is if you just plug in the values, minus 8.314 times 0.248, the calculate of 0.248 plus 0.752, which will divide by 0.752. That should give me 4.66 joule per Kelvin per mole. Okay, so this is actually positive. So upon mixing, my entropy is increasing. That's one point about. So I will put some more slides to solve this. Okay, next part asked us what is the total entropy of mixing? What is the total entropy? Now, this is the molar entropy, right? So the total entropy because it was calculated for molar entropy. It's the number, it's the entropy per mole. So total entropy of mixing will be equal to molar entropy of mixing times number of moles of solution. So we have the previous we have calculated is 4.66 joule per mole times 0.307 is the total number of moles of the solution, right? This will give me 1.43 joule per. This is the it's positive because we have the molar entropy of mixing is also positive, right? So what is the molar free energy change at 500 degrees centigrade? So molar free energy change at T is equal to 500 Kelvin or 500 degrees centigrade. Sorry. 500 degrees centigrade, right? So del G mix, which I've asked for change, so it is del G mix is equal to RT chi A minus chi A. For the ideal solution has been mentioned. We don't have the order parameter, so modulus. So this will give me delta G mix is equal to minus P delta S mix is equal to so we just multiply, so we add 273 to 500, we have 773 Kelvin, and negative of that 4.66 is the molar molar entropy for mixing. That will give me minus 3.60 to 10 to the power 3 joule per mole, and that is equal to minus 3.60 joule per mole, right? So this is again negative, so it favors the solid solution formation. And then the last part is what are the chemical potentials of gold and silver at 500 degrees centigrade, taking the free energies of your gold and silver as 0. Now, what are the chemical potentials, right? So mu AU is equal to GAU plus RT non RAU. Okay, so that will give me 0 as mentioned in the equation 0 plus 8.214 to 77 Kelvin times natural logarithm of mole fraction that we have calculated out to be 0.248. And this will give me minus 8.96 kilojoule per mole. So this is the chemical potential of gold. And similarly, chemical potential of silver will be calculated as GAG plus RT ln chi AG, that is 0 again, plus 8.314 into 773 into log 0.75, right? And then give me minus 1.83 kilojoule per mole. Okay, and coming to the last part, by how much will the free energy of the solution change at 500 degrees centigrade if one atom of gold is added? This your atom electron, limits very hard, it's very small, right? So for a very small addition, gold, we have dg prime is equal to mu AU dN provided the temperature, pressure and Ag is constant. So at 500 degrees centigrade, my AU was calculated as minus 8.96 kJ per mole. Now again, we know that so therefore we can get minus 8.96 kJ per mole is equal to minus 8.96 into 10 conversion factor for the volt divided by 16.3 is 23. This is easy per atom. So this is 1 here because we told that we are at 1. So local change is equal to the potential per units. This will give me minus 0.1 electron volt per atomic addition of volt. Right. So now we go on to the next question. Number 5. So it has been asked that show that the general expression for the chemical potential of the solution is given by this formula. So we know that UA is GA plus RT1 activity gamma A and phi A. Now how is this coming? Because AA is nothing but the product of the activity coefficient times the mole fraction of flow, right? Because that is the ratio that we assume. Where GA is actually the free energy of pure air, temperature T and pressure P, and GA, let's suppose it's known for a given temperature, pressure P0 and P0. So GA at T0 and P0 is, let's say, is given as GA naught. Okay. And from we also know that for 1 mole of A, dGA is Vm dP minus SA dt, right? So this, if my SA and Vm are independent of temperature and pressure, the change in temperature from T to T0 and change in pressure from T0 to T and change in pressure from T0 to T will cause change of GA as delta GA is equal to minus SA final temperature is T minus T0, initial temperature is Vm, final temperature is P, initial is P0, which is equal to, since we just open the bracket and we will substitute, which is GA naught plus delta G, right? That means give delta V GA naught plus SA P minus T naught plus Vm P minus T naught, and therefore UA, because if you remember, U can be written as G plus RT ln so GA plus RT ln gamma chi, right? So UA is equal to GA, which is using expansion, which is this, plus RT ln gamma A phi. Okay, then this activity of A by multiplication of times. Okay, so this is what we have been asked to prove, and we have proved that. Okay, now moving on to question 6. So it has been asked that the variation with completion of g-axis. G-axis is the axis free energy of liquid iron manganese alloys at 11863 Kelvin is given from this table here. So it's quite easy to see. Does the system exhibit regular solution behavior? Now, if we just take omega as the g-axis divided by I and then for each composition, so we just calculate. So what we do is we just divide each on the table and then we just take an average. What we get, the average of omega is about 4936 joule, right? And therefore, with respect to g-axis, the system is regular. So this is a regular system. Why? Because my x is greater than 0. My x is greater than 0. It's not 0, so it's a regular system. So this answers my part A. Now what does my part B says? We calculate the excess free energy, molar excess free energy of iron and molar excess free energy of manganese at a given mole fraction of manganese as 0.6, right? So the excess molar free energy of iron is given as, so let's take it here. All of it is coming from the formula, right? So I square, so 4396 times so 4396 joules times 0.6 square will give me 1.5 kilojoules. And the molar free excess energy of manganese is given by omega chi Fe is 4396. Its complement, so if we subtract 1.4, so it is 0.7 kilojoule. Okay, so that answers part B. And part C, calculate the activity. So this is basically activity coefficient. Delta G, not delta G, sorry. So gamma is delta G M and chi Mn is equal to 0.4, right? So that this is R into P into chi A ln chi A is 0.4 ln 0.4 plus chi B ln chi B plus omega chi A chi B, right? That gives me minus 9.37 kilojoule. This is less than 0 by 2, so it favors this addition. Okay, so we have answered this. Now moving on to the second last question. Okay, I have 8 questions. Okay, so lights in the lead tin system exhibit regular solution behavior at 473. So this is the activity and we have the fraction. Okay, and calculate the value of alpha. So what is this value of alpha? Right? So gamma is activity of lead by mole fraction of lead, which is 0.055 given, and mole fraction of lead is 0.1, which is 0.45. The omega value now will be value of R and ln 0.55 divided by 0.2, which is minus 4.578 kilojoules. So this is what we calculate the omega value, and then at 500 degrees centigrade, which is equal to 773 Kelvin, my pi SL is equal to 0.5. It's given in the question. So ln, since we're asking for the activity of it, so ln PSL is equal to minus 45. Which is minus 0.178. So we can get it by this exponential minus 0.178 times this 0.41. This is the activity of my 10 in the liquid solution of mole fraction of 0.5 at 500 degrees centigrade. So it's pretty simple. So coming over to the last question. So consider an ideal binary solution. So with mole fractions of equal mole fractions of A and B. The drop in the free energy of mixing it has been asked to calculate when the temperature is changed from 800 Kelvin to 900 Kelvin. Okay. So the change in free energy of mixing is given by this. Also given equal mole fraction, that is equal to chi B. Therefore, chi A is equal to chi B is equal to half. When they are equal and the sum of it is 1, so it has to be half, right? So that tells us that my delta G mix is equal to 8.314 times. I can directly take the delta P term. So we have 100 kelvins. So 1173 is 1073. 100 kelvins or 100 degrees centigrade difference, and 0.5 ln 0.5 plus 0.5 ln 0.5, and this will give me minus 576 joule per mole, which is equivalent to minus 0.576 kilojoule per mole. So this is the considered ideality, because we don't really have this omega term because it's an ideal solution, artificial solution, and this is our change in free energy of mixing. So we have seen the concepts related to the entropy, starting from the calculation of configuration entropy, and then we have seen how we can apply the calculation of entropy to find out the free energy, and then we have seen how the temperature changes, the chemical potential, the variation in chemical potential with the free energy, and what are the regular solutions, and how do you calculate the enthalpy of mixing, and we have derived the equation, and we have seen the slopes, and we have seen all the special 4 cases, right? And we went ahead with calculating the activity of solution on thermodynamic solution, and we have seen the ideal Raoult's law or non-ideal Henry's law, and yeah, and we have solved some handful of numericals that are related to the concepts we have discussed in this week. So if there's any doubt, you just leave me a question in the forum that is available on the NPTEL platform. So I'll get back with the clarification. So that was all. So I hope I'll see you next week, and have a happy learning period. Thank you.